Good morning everybody and welcome to today's webinar which is part 4 of our product design series, which will take us through some product design validation and simulation. So if we just take a look at the next slide, you'll be aware that the last few web series have been focusing on the design element of SolidWorks. We're going to take a look at the simulation element today. But in addition to the design and simulation, we've also got the ability to publish technical documentations, manage the data we create, and also run sustainability studies using SolidWorks products, which we'll take a look at in future webcasts. So as I said, this morning we're going to take a look at the simulation element. And if you just take a look at this little wheel here, it gives you an indication of the type of simulation studies that we can run with SolidWorks simulation. So we can do static analysis for assemblies in SolidWorks Premium. We can do frequency, thermal, fatigue, pressure and pressure vessels and drop test in Simulation Professional, and then dynamic and nonlinear in Simulation Premium. So if you just take a look on the screen now, just to sort of re-emphasize what I said a moment ago about which product suite the certain types of simulations fit into, that will give you an indication there of what we can do in each of those. Okay, if we just go back to the previous slide there, so what we're going to focus on today, we'll just switch over to SolidWorks, is the hose lock assembly that we've been looking at in the previous webcasts. And we're going to center around the main body of the assembly here, and we're going to run 2 studies on this one. The first one we're going to run is a pressure test, just to see if the wall thickness is suitable for the type of water pressure that's going to be going through the unit. And being a consumer product and a sort of outdoor device, we're also going to take a look at a drop test as well. Now, certain types of studies take a little bit longer than others to run, so the drop test is pre-run. We'll take a look at the results of those and the setup involved, and the pressure test tends to run reasonably quickly, so we can probably have a look at that one running through, no problem at all. So the first thing to notice about SolidWorks simulation is it's listed as an add-in. So if we go up to the add-ins here, you'll see simulation listed, and I've got that turned on. It comes with its own toolbar inside the SolidWorks window, so it's fully integrated into what we do in SolidWorks, which is a really nice benefit over some other tools. We don't have to change out of one application into another one, which is a real time saver. So if we go up to the top here, we can drop down our little arrow here, and we can use a study advisor, which will ask us questions about what we want to analyse, or alternatively, if we know the study that we want to run, we can just start a new one. So you'll see listed down the left-hand side of the type of studies that we can run. We're actually interested in a static study, but with pressure as a load. So we're going to create a new static study here. So we can click the green tick, and it takes us through into the simulation window towards the bottom here. You'll see that what we call the feature manager design tree is split into 2 sections. Now, the first thing we want to take a look at is invariably you'll work from top down to the bottom here in terms of setup. So I just want to click the plus next to the main body here and take a look at what's actually included underneath it. And you'll see, because of how we've modeled the actual casework of this part here, there's a number of surface bodies that we used as references. Now, we don't need those in our simulation study. And the reason we've got a little warning error there is because the thickness isn't defined for those surfaces. So we're just going to control select those items, and then we can exclude those from the analysis. So if you are working with multi-body solids or anything like that, you can actually exclude certain bodies from the analysis. And if you're doing it on an assembly as well, you can also exclude certain parts from the analysis if they're not adding any value for you. So the next thing we need to do is define a material for that solid body, and if we right click on there, we can apply edit a material if we haven't defined one in SolidWorks already, and go into the SolidWorks material database. Now, our particular part is made out of plastic, and it's made out of an ABS, So we can look here at the ABS plastic that SolidWorks lists in the material database and take a look at the properties that are included for that. You'll see here the red ones are the key ones, but also we need the blue values filled in, certainly thermal expansion if we're doing a thermal study. We do need yield strength as well for that material, which we don't have at the moment. A quick sort of search on Google can bring up a material data sheet. As you can see here, I've got a material sheet for an ABS material, and we can see that the yield strength is listed at between 42.5 and 44.8 megapascals, giving us an average of 44 megapascals. So we can fill that value in manually into our material database. It's worth pointing out at this stage that we're using SolidWorks 2013 here. In 2014, there's a new little section towards the bottom of the material database that allows us to go to a particular website and acquire simulation materials for use in these studies. So quite a time saver and quite a good improvement in the 2014 suite of products there. I can't show you that at the moment, but we'll be talking about that at our customer day coming up at the end of October. So if we want to fill the information in for the yield strength for ABS, what we really need to do is copy that material and create a custom material, which I've already done towards the bottom here. So if we look in the plastics folder, we've got an ABS material with the yield strength filled in there for us. So we're going to apply that material to our part and close that down. And you'll see once we've done that, we get a green tick indicating that the material is defined okay. If we move down to the next section, that includes connections. So if we were analysing an assembly, we would need to define some contacts between items. In this case, we're analysing a single part, so we don't need to define any contacts. So we can move on to the next stage, which is the fixtures that we need to add. So we need to ideally fix the item in space so it's not going to float off. So we can right click on here and add some fixed geometry. So I'm just going to fix the base set of faces here just to hold this item down. You know, it would be attached to some kind of hose linking section at the bottom here, so a realistic fixture, but we could equally fix it up at the top here on this hinge point if we wanted to. And we can just add that fixture on like so. And you'll see that the symbols indicate that that face isn't going to move. So we're not going to see any movement in and around that area, but we may see some stress concentrations there. If we do, we may need to think about moving that fixture elsewhere. Because this is a pressure test, we're going to be adding an external load and we're going to be adding a pressure. So we can choose pressure from the drop down here. And we want to pressure internally on all the faces, so it's going to be normal to those selected faces, indicating the water pushing out on the inside faces for us. So if I go ahead and we'll have a look on the inside here, you can see there's a number of faces because of how this was modelled. So we'll just go around and we'll select each of these faces here, indicating an internal pressure on those faces. Like so. And we could also include some of the faces at the top here as well if we want to, like so. So we'll just do both sides. You can see the arrows indicate the pressure acting normal to those faces. We then need to fill in a pressure value, and typical sort of household water pressure from an outside tap is around 2 bar. Which, if we convert that to PSI, is about 30. So we can fill in 30 PSI here for the load that we're adding. If we click the green tick there, that will add that external load. Really, the next thing we need to do is apply a mesh, as we do in every simulation. And we can use the automatic settings for this if we want to. So if you right-click on here and say Create Mesh, it will bring up our meshing window with a very simple slider at the top, which will allow us to define either a coarse or a fine mesh. So we can drag that slider up and down, which will adjust the type of, or the coarseness of the mesh that we're adding. What you can also do is go into the mesh parameters, so we could actually manually set values for the size of elements that we're going to be creating. So because we're working on quite a curvy product, we're going to switch to a curvature-based mesh here, and we'll just adjust some of these values here. So typically what you would do with any simulation is sort of work through what we call a convergence procedure. So we would start out with a reasonably coarse mesh, run a study, look at the results, write those down, and then refine the mesh after that point, and again then take a note of the results that we're getting. And you would proceed to do that a number of times until the results don't get any more or don't get any change in them. So we would say that the mesh has converged at that point. We haven't got time to run through that process, so I'm just going to drag this slider along here, and we'll say that we'll have a mesh element size of, let's say 2 for argument's sake. There is also a minimum size that is linked to that maximum, and we've got some other controls under here, so we can control the number of elements around the circle and also the growth ratio of the elements as well. So if we click the green tick, that's going to go off and generate a mesh for us. So you'll see the mesh window comes up, and that's using a certain amount of memory there. It's quite a quick meshing process depending on the settings that you've specified, so we should see some results on the screen in a moment. And we can see here that the mesh is generated. So if we take a look around, ideally we're looking for 2 elements through the thickness. We've got sort of 1 here, so we may want to refine that a little bit more. We've got quite a few in and around the curved areas, but for the time being we'll leave that as it is, just to give you an indication of what we can do with these type of studies. So once the mesh is done, really all is left for us to do is actually run the study. So we can right click here and run. It does take a little while, so we're going to switch over to a pre-run one and take a look at some of the results. Okay, so if we come over to our pre-run study here, we can take a look firstly at the stress, so we can just activate that plot so we can see what's happening with that internal pressure. So we'll load that up and we can take a look at the deformed result of the model. Now this is amplified to quite a scale. At the moment it's 71 times amplified, but really what we're looking at here is the von Mises stress, so we can have a look at what the highest stress is in the design here at 24 megapascals, and from that we can work out what the factor of safety is. Alternatively, we can use the system to generate a factor of safety plot for us. So if we go to the factor of safety plot, which is generated at the bottom here, we can take a look and see what the factor of safety is in our design. Really we're looking for around the 2 figure. And we can see that we've actually got a minimum factor of safety of 1.8 in this particular design. So we may need to do a little bit of rework on the casing just to strengthen that up in certain areas, or alternatively increase the wall thickness, or look at changing the material. There's a number of options we've got there, but we are quite close to that 2 number, so it would only be subtle changes that are required. If we want to analyse in a little bit more detail as to where the stresses are, we can switch back to our stress plot and use some of the nice options that we've got to actually analyse those results. So the first one we've got here is ISO clipping, which will, if we just hide the simulation symbols just to make it a little bit easier to see what's going on, we can actually drag the slider around and start to understand where the highest stresses are in the design here. So we can start to see that the majority of the problems are on that main casework there, so we may need to look at strengthening that up. So there's some quite nice things we can do with ISO clipping. Another thing that we may want to look at is the displacement in our design, so we can double click on the displacement plot and take a look at that. And you can see that the highest displacement here indicated by the red sections is shown. And if we take a look at the graph just to try and understand what the maximum displacement is, we can see that that is currently 0.18 of a millimetre, so not a huge amount by any stretch for this type of product. Okay, so that gives us a brief sort of look at the type of pressure test that we can run on this type of product. The next study that we want to maybe look at for a consumer product is a drop test. So again, from the top here we can drop down and create a new study. We want to create a drop test, so we can add that one in like so, and it takes us through to the drop test study that we're going to run. So again, very similar to the static pressure test that we ran, you work from the top down to the bottom. So we're going to right click on the component and apply the material. So it's going to be the same material that we're using, which is ABS. So we'll apply that material to the product like so. It gives us a green tick. We haven't got any connections in our design here, so we don't need to add any of those. And we're just going to skip the mesh section because we've already looked at that. The next thing that we need to do is take a look at the setup for the drop test. So if we take a look at the property manager for this here, we've got a number of things that we can do for drop tests. So the first one we can do, which is actually what we're going to be interested in, is dropping from a height. So we can simulate this product being dropped from a height. So if we're doing that, we move on to the next section here, which is height, and we're going to be measuring from the origin, effectively, of this component, and we're going to drop it from 1,000 millimeters, so we're going to drop it from 1 meter. So the next thing we need to do is then indicate where, in which direction gravity is acting, so we can understand in which direction we're actually going to be dropping this product. And you can do this a number of ways, really. If we just take a look at some of the planes we've got in our design here, we've got the front plane. So let's say we were going to be dropping it in this direction, coming down, which is actually what we've done in the pre-run study. The item is going to hit a plane at a meter down, effectively, from here. So we're going to see it impact at this point first. But if you wanted to look at more angular drops, you know, or on a different area of the design, you could create some reference planes at a slightly different angle, and you can then drop onto that plane. It just depends on where you create these reference planes. So we've indicated a front plane. We've specified gravity in the direction that's moving in. We can then specify the target orientation, so it's normal to gravity or parallel to a reference plane, as I mentioned. We can also indicate that we're working with a flexible target if we want to, so you can do things like that as well. We're actually going to use a rigid target. You can also specify contact damping as well, so if there is a ratio of damping that occurs when the product hits a solid object, you can specify that as well. That's pretty much all we need to do within the setup for the drop test there. The next thing we need to do is define some results options. So the most important one, and this does impact on the solve time that will happen. So these drop tests typically take a fair while to run. So we can limit the time after the impact that's measured by the system. So here you can see it's 92 microseconds by default, but you know, I'd probably change that to around 50 microseconds, and then that's going to have a direct impact on how long the study takes to run. We can also specify to save the results from a particular time step, or alternatively, if we leave that at 0, then it's just going to log the data from the, from the second of impact there. And we can also specify some sensors to measure as well. So, for example, if you're looking at an electronics enclosure with damage susceptible components, what we could do is add a simulation sensor into the area of interest, and then look at the data for that sensor across the time steps that we've generated. Okay, so once we've set those results options, we can then go ahead and run the study. Typically, as I said, these do take a little while to run, sort of a good few hours depending on your machine. So if we refer back to a previous test that's been run, we can take a look at the results for this. So if we have a look at the stress impact, we'll just load that plot up now and take a look. As I said, the majority of the stress is going to be focused in and around this area because that's where the impact occurred, like so. So we can see here that we've got quite a high stress in that area, 31 megapascals. So, you know, it's very close to yield at that point. So again, we may need to look at choosing a different material or strengthening up in particular areas where it's a little bit weaker. You can actually animate these as well. So if we just let this generate here, it takes a little while to put all the frames together for the animation. So we'll just let that work itself out. We can see that we get an animation of the product actually dropping from its designated height onto the plane, so we can start to see how the stress actually transfers through the product at the drop point. So as I said, if you wanted to, we can adjust the plane that it's going to hit in terms of an angle, and then we're going to get a more angular drop, because invariably with something like this, it's not going to drop flat like that onto the floor. It will move. We can save these out as AVI files as well if you want to show people. And interestingly enough, all the simulation data that we accumulate in these files, if we do save an e-drawing of these parts or assemblies, those simulation plots will go through to e-drawings as well. So if you are looking at communicating these between colleagues within the office or people externally to your business, e-drawings is a really, really nice way to do that. So we can add additional plots in here, but principally we're interested in the stress and displacement of the plastic. It may be that we need to do a slightly more advanced study on this here. So if the plastic is deforming permanently, we may need to look at a non-linear analysis. And if we just refer back to our product matrix here, you know, if you want to do non-linear analysis, that would require a step up to simulation premium to do that type of study, but it's certainly possible. Okay, so if we just move on to the next slide, in fact, if we just go back, we'll just summarize what we've looked at. So we've taken a look at two particular studies. We've taken a look at our pressure test first and foremost to analyze whether the product is suitable to take the internal pressures of the water that we're working with. And then we've taken a look just for validation that it's fine if we drop it from a certain height. So we may want to follow that up with a physical drop test, but we can see very early in the design process whether or not it's suitable and whether or not it's going to fail. Moving on from this, in the next section that we're going to look at, we're going to be taking a look at the internal flow on that particular device. So we'll try and understand how the water is going to flow through that, which is on the 10th of October. Again, sort of following on from that theme, on the 17th, we're going to be looking at whether or not our material choices are sustainable, and then also analysing whether or not the product can be moulded. So we have a tool in SolidWorks called SolidWorks Plastics, which will analyse the plastics flow whilst it's being injected. Then on the 24th, we're going to take a look at creating moulds for manufacture. And then we've got a break on the 31st, but we're back on the 7th of November to take a look at creating instruction manuals with SolidWorks Composer. So what we'll do now is we'll just take some questions on what we've seen. So if anybody has got any questions, then you know, you should be able to fill those in on a little section there. If you can just send those over, I'll do my best to answer those for you. But if you haven't, thank you very much for watching, and we'll see you again next week.